Okay, so the last part of today's class is again a quick activity on conservation of energy. These are the parts that we usually do it in the problem, but now like we're looking into the pieces separately. Okay, so we have an example. Again, it's an experiment. A cart will travel down the frictionless surface. So we are this displacement is down the incline, and the angle theta is given. Again, x and y are given just to kind of show you that little triangle there, and the position coordinate x is measured away from the sensor, so the sensor is right here and along the ramp. And using the picture, we will develop an expression for the height of the cart. Okay, so this is what you do when you have an inclined surface. You do relate x and y, as we did an example earlier. So using the geometry, sine theta is opposite over adjacent. So we are going to use that, and you can see that opposite is y, and adjacent, opposite over hypo, so it's going to be y over x. And rewriting this for y, it becomes x sine theta. Okay, so that is how we relate x and y. Next, we want to now, using this answer, we want to develop an expression to calculate potential energy of the cart based on its coordinate. So we have an elevation change. That means we will have gravitational potential. It's in the form of mgy, and y is x sine theta. So we are just simply using that for y, and we are getting u equals to mg x sine theta. Later, we are going to kind of put these together, and now we are going to apply conservation of energy to the card. And we'll simplify as much as possible first of all. So we are writing the energy conservation equation first, as you can see it in here. And then we're going to cross out the terms that are zero. So there's change in velocity or speed, and there's an elevation change. We're keeping those. There's no spring. Delta UE is 0. Delta I is 0 because there's no temperature or pressure changes. And there's also no friction to change the temperature as well, so that goes to 0 too. And there's no heat transfer. So we then end up with having delta K plus delta UG equals to work done, as usual. Okay, so we do simplify it first. Next is drawing free body diagram. We have weight force downward, normal is perpendicular to the surface. And we have also drawn the coordinate system, Cartesian coordinate system. After that, we are going to find the total work done. Okay, so that's the right side of this equation. And let's find that out. Since we have two forces only on the free body diagram, we have two terms in the work term. But we already use this as delta UG, so we are getting rid of the work done by the weight force, and it's the potential energy. And the normal force doesn't do work because it's perpendicular to the motion. Okay, that goes to 0 as well. That means there is no total work, and the right side is going to be simply 0. Left side is delta K plus delta UG. So this tells you for this problem, when the object is sliding down on a frictionless, again, that's important, frictionless ramp, what happens is then the change in kinetic energy plus change in potential energy should be 0 when you add them up. So they should kind of complement each other. Okay, so then we are working on the plots, and we're going to think about individually what happens to kinetic energy and what happens to potential energy, and then what happens to the addition of those two. Okay, so initially kinetic energy starts from 0 and sliding down, and that's why we start from 0 kinetic. V is 0, that's why. Okay, and we know that K is in the form of 1/2 mv squared. Okay, and the potential energy is, again, we only have gravitational potential, we are talking about mgy. but we are also thinking about like how is it changing with time. Okay, so kinetic energy is going to be a quadratic equation, because one way to understand that is like looking at the next step. So kind of if we had the experiment and like finding that those plots, and then how would you kind of prove this? You would use the constant acceleration equations, okay, because acceleration is constant in this problem. So what you see is velocity is linearly proportional to time, but kinetic energy is quadratic. That means you're going to get a quadratic equation for kinetic energy. And kinetic is increasing because velocity is increasing, okay? And here you see that potential is linearly proportional to y position. But what we have is this position equation for x. It's also true for y. Y is proportional to time in a quadratic form. Okay, and one other thing that's important is, since the acceleration is down the incline, but we said up the incline is positive, acceleration is negative. Okay, so what that means is the potential term is going down. Okay, so we have a initially maximum potential, and if you reach zero potential, if you say the bottom level to be 0 y. Okay, so you need to kind of mention that, and we don't have it drawn here, but that would mean actually we kind of have it here, sorry. Yeah, we have that y starting from here, that is y equal to 0. Okay, so I don't have to draw it again. And but when you see it at any point, okay, if you like look at right here, let's just take this point. I'm gonna go also 2 blocks and take that. When you add these points up, you're getting that. Okay, so just like it becomes 3 block size. If you look at the initial point, so these 2 points, kinetic is 0, and then potential is 3 blocks. When you have that, again, you are right here. Any point you choose, you get the same value when you add up kinetic and potential. And it is because of this equation here. Okay, so we're kind of proving that when you add up change in kinetic and change in gravitational potential, it should give you no change. So that means K plus UG should be constant number. Okay, so that's what we see. It's constant. You see that line? And that's also called mechanical energy is conserved. But again, you don't have to worry about the terms like that. And the equation really comes from the general conservation of energy equation, so you don't have to memorize anything. Okay, and the rest of this, we are going to stop it here for this class, and the rest of it will be discussed on Monday.